Millions of people are about to spend their holiday staring at the bumper in front of them. You're sitting there, losing your patience, and you look over at the lane next to you. It seems to be moving, so you signal, drift over, and expect to finally make some progress. But almost the second you merge, you slam right back on the brakes. Your new lane grinds to a total halt. You peer through the windshield, looking for the reason. You expect to see flashing lights, orange construction cones, or a bottlenecking lane closure. But there is no accident. The road ahead is completely clear. You are stuck in a queue that seems to exist for absolutely no reason at all. Traffic researchers call this a phantom traffic jam. A phantom traffic jam is a start-start wave that ripples backwards through a highway, even though every single vehicle is trying to move forwards. When you're caught in one of these waves, it's easy to assume the driver at the very front must have made a mistake, or that everyone else on the road just doesn't know how to drive. The math tells a very different story. That lane change you made to get yourself home a few seconds faster is exactly the kind of maneuver that created the jam in the first place. In 2008, a team of Japanese researchers placed 22 drivers on a circular track. The instructions were incredibly simple: maintain a constant speed and keep a safe distance from the car in front of you. Within minutes, the system degrades. One driver brakes slightly more than necessary. The driver behind them reacts a little later, which forces them to brake a little harder. The next driver does the same, and the initial tiny disturbance grows. It travels backwards around the circuit, forcing drivers behind to stop completely, despite there being no obstacle anywhere on the road. Our reaction times are imperfect. These tiny variations in human behavior act as noise, slowly degrading the entire traffic network until it collapses. To figure out how to stop these waves, mathematicians stop looking at individual drivers and instead treat traffic as a continuous flow, much like fluid dynamics analyzing water moving through a pipe. This equation shows the core relationship in traffic flow theory. Q represents the total traffic flow, or the number of vehicles passing a specific point per hour. That flow equals the traffic density on the road multiplied by the average speed of those vehicles. The upward curve on this graph shows the obvious initial logic. Adding more vehicles to an empty highway naturally increases the overall flow of traffic passing through. But look closely at the peak of the curve. This represents the optimal traffic density. Once the road gets too crowded past this point, drivers are forced to slow down. The severe reduction in speed easily outweighs the sheer number of cars, plummeting the overall flow downward. Cramming more cars onto a highway doesn't mean more people get home faster. Past that exact tipping point, maximizing the raw number of vehicles actively destroys the efficiency of the entire road. This exact tipping point is why your decision to constantly change lanes in heavy traffic is rarely worthwhile. When the highway is already near peak density, merging creates a small disturbance. The driver now behind you has to brake to maintain a safe following distance. The driver behind them reacts a little slower and a little harder. By trying to secure a tiny momentary advantage for yourself, you introduce the exact micro-disturbance needed to spawn a stop-start wave. Your clever maneuver guarantees a slower journey for the entire network, including you. Applied mathematicians use control theory to keep unpredictable systems like this stable. By taking noisy, incomplete live data from road sensors and cameras, they can coordinate decisions to prevent these traffic waves from ever forming. To prove this works in the real world, researchers repeated the Japanese circular track experiment in 2018. They kept the human drivers, but replaced just one vehicle with a single autonomous car. That autonomous car was programmed to accelerate and brake perfectly smoothly. Instead of overreacting to the cars in front of it, it absorbed the stop-start shockwaves, acting as a physical dampener for the entire track. That single vehicle made up less than 5% of the traffic, but it successfully eliminated the phantom jam. You don't need total control over every car to stabilize the network. You only need a fractional strategic anchor to cancel out human volatility. While we wait for connected autonomous infrastructure to become the norm, you can adopt the exact same algorithm. Maintain a safe following distance, accelerate and brake smoothly, and resist the urge to keep switching lanes. The fastest way to your destination is not driving aggressively. By suppressing the selfish instinct to inch ahead, you keep the flow stable, ensuring the whole system gets exactly where it needs to go.